Good afternoon, everyone. My name is Yong-un Che, and I'm glad to introduce my work, Graphics-Aware Power Governing for Mobile Devices. I will briefly introduce my co-authors, and I'm the first author, and the second author, Sung-hoon Park, and my great advisor, Professor Ho-jung Cha. First, I'll discuss the importance of the energy optimization for mobile devices. During 10 years, the AP has been 20 times faster and the display resolution has been 10 times higher, but the battery capacity has only doubled. Due to these unbalanced advances, efficiently using the limited energy is a very important problem in mobile devices. One of the most energy-consuming tasks in smartphone is graphics, drawing frames on the screen. Let's look at this pie graph. Many previous research studies discussed three main components consume the most of smartphones' energy: CPU, GPU, and display. These components are deeply related to the graphics. Recent smartphones draw 60 frames per second. This means that each frame should be completed within 16.7 milliseconds, as failing to meet these deadlines degrades the quality of users' experience. Modern graphics pipeline actively exploit both CPU and GPU to accelerate this frame rendering. It increases the device's power demand, so the energy optimization of graphics pipeline is very critical. Then, how to reduce the energy consumption of graphics pipeline? The key power-saving feature in mobile is dynamic voltage and frequency scaling. This feature controls the operating voltage and frequency of the processor at the same time to reduce the energy. As shown in this graph, the operating voltage of the processor is proportional to the operating frequency. So even if the same task is executed, the energy consumption can be lowered at the lower processor's frequency. Existing systems control this DVFS by using individual DVFS governors. For example, CPU is controlled by CPU DVFS governors such as interactive, on-demand, or schedule, and GPU is controlled by GPU DVFS governor, which is optimized by manufacturers. But these governors are basically based on the loads which are measured by the system, but without knowing what they are really processing. So without that, without that, this kind of energy optimization should be based on the knowledge about the task itself. So we first started with the understanding of the graphics pipeline itself. This is the overview of the Android graphics pipeline. Frame rendering is a very complex process from VSync to the display. This process consists of the UI thread, render thread, surface flinger, hardware composer, and GPU. UI thread determines what should be updated in the screen, and render thread requests the buffer to the surface flinger and generate the GPU command. And GPU executes these GPU commands to draw frames, and surface flinger holds these frames, and when VSync occurs, this frame is delivered to the display device via hardware composer. I'm skipping the details in here, and this graphics pipeline can be divided into two tasks, which is executed on the CPU and which is executed on the GPU. So this graphics pipeline can be simplified like this. And from VSync, CPU and GPU tasks are executed in order, and after GPU task is completed, the graphics pipeline waits for the next VSync. When next VSync occurs, the drawn frame is delivered to the display. Without that, reducing this wait time may lead to energy reduction. In terms of DVFS, this hypothesis seems to make sense and is consistent with our main philosophy. High-level knowledge of the task can lead to the better DVFS control. But we should first check whether this wait time really exists in real applications. We measure the frame rendering time while running 60 real applications on real device. The results show that the most of frame renderings are completed much earlier than the deadline. Particularly, 75% of the frames are rendered within only 8 milliseconds. To understand why frames are completed so quickly, we experimented with one target application, Google Now Launcher. Similar to the previous research, we can also observe that the frames are completed much earlier than deadline, and graph below shows that the graphics-related processes were run by using the high CPU frequency in little cluster, and particularly, UI thread and render thread are also run at the big cluster. From this research, we suspected that high CPU frequency and the big cluster might be unnecessarily used. To verify this, we implemented some simple CPU DVFS governor. This governor is optimized to the previous experimental scenario by brute forcefully finding the optimal CPU frequency for each frame. Note that UI thread and render thread are fixed to the little cluster. And let's look at the graph below. That with this governor, the frame renderings are completed within the deadline without using the big cluster and only using the lower CPU frequency in little cluster. So from this research, we can find two problems: overutilized CPU frequency and overutilized big cluster. From our analysis, these problems are caused by some efficiencies in components which CPU DVFS touch boosting and being leader scheduling, but I'm skipping the detailed analysis research in here, and you can find that this explanation in our paper. And we also noticed that the Android graphics pipeline was divided into CPU and GPU tasks. In this experiment, we also controlled the GPU frequency as well, while lowering the CPU frequency as in the previous experiment. As shown in this graph, we could find a new optimum point which can further reduce energy. At this point, although the GPU frequency was raised one step, but the total energy consumption can be reduced by lowering the CPU frequency further. From this research, we can find the additional problem of the existing system, that independence of GPU DVFS governor. So in summary, we observed the energy inefficiencies and the causes of that from the motivational experiment. First is the high CPU frequencies are unnecessarily used. Second is the existing system was utilizing big cluster. And third, due to the independence of the GPU DVFS governor, the existing system are CPU and GPU frequency setting. So solutions are corresponding to each problem. VSync aware CPU max capping, graphics clustering, and GPU min capping. Our first solution is that VSync aware CPU max capping. This solution tries to delay the completion of the frame rendering closer to the next VSync by regulating the maximum CPU frequency. This maximum CPU frequency regulating is called CPU max capping. And by doing so, our solution can be easily implemented to the system and can coexist with the existing system's governor. So as this existing system's governor is optimized by manufacturers for general purposes, therefore, this coexistence is safe choice to guarantee the performance of other background processes. And our second solution is graphics clustering. This solution tries to run all of the graphics-related processes in the little cluster whenever possible. As CPU frequency is controlled by in cluster unit, not in core unit, if the graphics-related processes are run on the different cluster, so controlling the frame rendering time becomes very difficult. With this solution, graphics-related processes are executed in the same CPU cluster and their execution time can be identically adjusted by the same governor. So this solution helps the previous solution, the VSync-aware CPU max capping, to work correctly. And our final solution is the GPU min capping. As the existing GPU DVFS governors tend to use the GPU frequency as low as possible, so we raise the minimum GPU frequency. With this solution, we can accelerate the GPU task and make the completion of the frame rendering much earlier. And as a result, we can further lower the CPU frequency by delaying the CPU task more. However, these solutions are just an abstract concept, and applying them into the real system is another problem. To implement our solution in real mobile systems, we integrated them into the single framework, GFX Governor. This is the overview of our GFX Governor. GFX Governor designed as a layer above the CPU and GPU governor inside the kernel, and it receives the high-level information about the Android graphics pipeline from the Android framework and properly apply our abstract solutions, which is the VSync-aware CPU max capping, graphics clustering, and GPU min capping. And GPU governor consists of two main components: frame load predictor and VSync-aware DVFS controller. First component is the frame load predictor. We define the frame load as the sum of the load of CPU and GPU, and the load of processor is defined by the estimated execution time of given load at a minimum processor's frequency, like this equation. And this is somewhat heuristic definition, but it is the compromise for the minimizing the overhead. And predicting next frame load is based on the assumption that the content once we adopted the exponentially weighted moving average model for prediction for the load tracking problems like is VSync-aware DVFS controller. This controller and GPU frequency. Our goal is bring the user to QoE. This while meeting the deadline, and this equation theoretical optimum point where but as the CPU and GPU frequency is discrete in real mobile system, so the point where the optimal frequency of CPU and GPU exists is existing somewhere different place. So that we developed that to find this actual optimum point in real time. So the detailed algorithm is described in our paper. And we implemented and evaluated this GFX governor on 3 Android reference smartphones, and 60 applications from various categories are used in our experiment. And the power consumption is measured by the monsoon power monitor. We first evaluated the accuracy of the frame load prediction. The results show that most of applications showed high accuracy, over 90% for all the devices. And after that, we evaluated the effectiveness of our GFX governor in 2 aspects: energy saving effect and the quality of user's experience. And as shown in the left graph, the GFX governor successfully delayed the completion of the frame rendering near the deadline. And we can see that these delays can be lead to the real device level energy saving, as shown in the right above graph, so about 20% on average. And the number of number of frames which cannot meet the deadlines are not increased on all three devices. So from this result, we can verify that the GFX Governor improves energy efficiency without degrading the quality of user's experience. And we conducted further case study experiments for 3 applications: Google Now Launcher, Pinterest, and Google Chrome browser. Google Now Launcher has some high frame load prediction accuracy due to its steady frame load, and after applied the GFX Governor, the frame rendering time was moved to the closer to the next VSync, and that this leads to the lower frequency of the CPU by CPU max capping and the reduction of the big cluster usage by graphics clustering, and these can be leads to the finally energy reduction. And in the case of Pinterest, Pinterest has the slightly lower frame load prediction accuracy than the previous case due to its somewhat dynamic frame load. But although the few frames vary to meet the deadline, but the frame rendering is completed until most of the frames are rendered until the VSync. And of course, the completion time was also moved to the closer to the deadline, and another results are similar to the previous case. And Google Chrome browser has the very dynamic frame load, therefore it has low frame load prediction error, and compared to Pinterest, more frames are failed to meet the deadline. But even in this worst case, we can verify that our system can reduce the energy. And we also evaluated whether GFX Governor is effective in devices in which energy-aware scheduling is enabled. Energy-aware scheduling is the state-of-the-art CPU power management technique which combines CPU scheduler with the CPU DVFS governor, and the figure A shows that the 6 trace of the EAS-enabled system and frame rendering time is also earlier than the deadline, and although the little cluster is only used, the frame rendering time is also earlier, and after using our GFX governor, the frame rendering time is delayed near the deadline, and this can be lead to the energy reduction. In conclusion, we first observed the energy inefficiency in real system and suggested that solutions to solve that and implemented them as the GFX governor, and finally verified the effectiveness of the GFX governor. We'd like to finish my talk by introducing our future work. We plan to extending our GFX governor to the dynamic queue, a new big little architecture recently introduced by ARM, and we are preparing the papers about the energy optimizing other kind of applications which uses their own graphics pipeline, because for example, game applications are their own graphics pipeline to draw the frames instead of Android graphics pipeline. Thank you for the listening.